All right. Hello, everybody. Today we're going to go over Chapter 8 on your book, which is on metamorphic rocks. Metamorphic rocks are formed from the alteration of any rock with heat and pressure. Metamorphism usually occurs in this area of the rock cycle. So, as you can see, sedimentary, igneous, or other metamorphic rocks can metamorphose and have further alteration or transformation. So unlike igneous and sedimentary processes that occur in the surface and near the surface environments, metamorphism most often occurs deep within the earth. So this depth is usually beyond our direct observation. At such depths, this pre-existing rock of any of the three types is altered by high heat and pressure. Those are the main two things that affect it. And under those conditions, it is where alteration or transformation takes place. And this can be done through deformation, it can be done through recrystallization, or it can be done through both of those things together, as we will see later in the chapter. Oh, from this image, this slide, I also wanted to point out this image right here. Here I'm showing you what the recrystallization looks like. So the small minerals that are kind of circular here, those are garnets, which are usually a form of recrystallization from other minerals that are not metamorphic. And then the deformation looks like these type of folds that we have over here, where the mineral composition remains the same, but there's a reorganization of the crystals. So, because every metamorphic rock comes from another rock originally, each metamorphic rock has what we call a parent rock. In this slide, for example, both granite and sandstones transform into gneiss. So, gneiss has two potential parent rocks in this example, which can be granite or sandstone, for the most part, arcosic sandstone. Okay, so metamorphism itself means to change form, and it is a process that transforms the mineralogy, the texture, and sometimes the chemical compositions of the parent rock. The mineralogy, or mineral constituents from that rock, changes because the rock is subjected to new conditions, usually these conditions being elevated temperatures and pressures, which are significantly different from those in which it initially formed. For example, kaolinite, which is a clay mineral, and as we saw in chapter 6 and 7, clay minerals are stable at the surface themselves. Kaolinite will transform into chlorite or muscovite, which are different minerals, when the rock in which this kaolinite is metamorphosed. Under even more extreme conditions, the chlorite that transformed from the kaolinite will actually become biotite mica. So you will end up with muscovite and biotite. Metamorphism also alters the rock's texture, which produces large crystals for the most part, and sometimes distinct layering or banded appearance, which we will touch on later. The degree to which a parent rock changes during the metamorphism is called its metamorphic grade, and it varies from low grade, which is low temperatures and pressures, to high grade, which is high temperatures and pressures. For example, in the low grade metamorphism environment, the sedimentary rock shale, which we looked at in chapter 6, becomes the more compact rock slate. Here, the clay minerals in the shale transform into tiny muscovite and chloride flakes. Sometimes differentiating between a shale and a slate is not an easy task, which illustrates that the transition from a sedimentary rock into a metamorphic rock is oftentimes gradual and the change is somewhat subtle. So in high-grade metamorphism, metamorphism sometimes causes a transformation so complete that the identity of the parent rock cannot be easily determined. In these types of environments, features such as the bedding planes, or fossils or vesicles, meaning pore spaces, that existed in the parent rock, will no longer be in the metamorphic rock that results. And furthermore, the rocks typically get deformed due to the great compressional stress, and hence they typically experience folding, like the one that you see in the image on the top, for example, right here. So those are folds. The image on the bottom right here of the slide shows a relationship among metamorphic, sedimentary, and igneous environments in terms of temperature. So overall, metamorphism occurs at a range of temperatures that lie between those experienced during the formation of sedimentary rocks and the temperatures that approach those at which igneous rocks begin to form, or at which rocks begin to melt, that later on become igneous rocks. So the temperatures at which metamorphism occurs are typically somewhere between 200 and 700 degrees Celsius. It is important to also reiterate that during metamorphism, the rock remains essentially solid. There might be a little bit of deformation, so the properties may be good enough so that there is a little bit of change, plastic change, but there will not be melting. If there is significant melting, the rock has entered into the activity of igneous rocks per se, into that realm. Along with temperature, pressures is going to play a very important role in metamorphism, compacting the minerals to a degree where they will be more compact and have more crystalline structures. So typically, metamorphism is going to involve the formation of new minerals from pre-existing minerals. So there is a recrystallization, a changing of those mineral compositions. Or not compositions, just the minerals themselves. So what drives metamorphism? What are the agents of metamorphism? The agents of metamorphism are heat, pressure, or I should say confining pressure, differential stress, and chemically active fluids. So during metamorphism, a rock may be subject to all four simultaneously. However, the degree of metamorphism and the contribution of each of those agents may vary from one environment to another. The most important factor that drives metamorphism is going to be heat. Heat is the most important one because it provides the energy that is needed to produce the chemical reactions that result in the recrystallization of existing minerals. So, if you remember from chapter 4, we discussed that with an increase in temperature, the atoms within a mineral begin to vibrate more rapidly. And we also saw this in chapter 3. So they will begin to vibrate more rapidly, even if still under a crystalline form, where the atoms are strongly bonded. So this elevated level of activity that you're seeing in the atoms allows individual atoms to migrate more freely between sites in a crystalline structure still. So the formation of new or enlarged mineral grains at the expense of the original grains is called recrystallization. So during this process, the mineralogy of the rock may or may not change, but the grains tend to always become larger. So this is what happens when quartz sandstone, for example, metamorphoses into quartzite. Both of them are made out of quartz grains, but in the case of the metamorphosed rock, the quartz grains end up being larger and they end up being fewer. Although the mineralogy overall changes in the transformation from shell to slate, for example, the overall chemical composition remains essentially unchanged. So the same elements that made up the minerals, the clay minerals that were in the shale, are the same elements that are making up the minerals in the rock slate. So these new existing atoms that are in the metamorphosed rock are rearranged into new crystalline structures that are now more stable in this new environment of high heat and high pressure. Okay, so there are two primary ways in which a rock may become hotter. The first one is it may become more deeply buried, and as we saw in chapter 4, the Earth's temperature rises with depth. The second way is that it may be heated by a nearby magma body. So those surrounding rocks may be close to a magma body that is heating them up. So let's examine the first scenario now. As we know, the Earth's interior is extremely hot, and this is mainly because of the heat that is released from the repeated collision of asteroid-sized bodies during the formation of our planet. But it is also due to the energy that is being continuously released by the decay of radioactive elements. And we'll look at this in chapter 18 in more detail. But as you also saw in chapter 4, the rate of increase in temperature with depth is known as the geothermal gradient. And in the upper crust, this increase in temperature averages about 25 degrees Celsius per kilometer that you get deeper into the Earth. So, minerals like the clay minerals in the shell experience deformation and recrystallization at about 8 kilometers depth, or 200 degrees Celsius. Other minerals like quartz and feldspars don't experience recrystallization, but they do experience changes in their texture. However, these changes in texture, this deformation that occurs to them, occurs at much greater depths and temperatures. The second heating mechanism is from nearby magma emplacements, as I said earlier. In this case, the heat is transported from the mantle into the shallowest layers of the crust by that magma body that is rising due to being less dense. The image in this slide shows several examples of conditions in which heat drives metamorphism from either of the two heating mechanisms. Environments where rocks may be carried to great depths and be heated include convergent plate boundaries, where the slabs of sediment-laden oceanic crust are being subducted. Rocks may also get buried deep in large basins, for example, where gradual subsidence, so meaning burial by the overlying sediments, will result in thick accumulations of that rock. Some continental collisions result in mountain building events, for example, which cause some rocks to be uplifted, while other rocks are being thrust downward, where elevated temperatures and pressures trigger the metamorphism. And then there are places where metamorphism is caused by the heat from the nearby magmas, which can occur at areas where there is a rising mantle plume, or in the upwelling of mid-ocean ridges, for example. And the magma generated from the partial melting that occurs at subduction zones as well. So, as you can see, this high heat and high pressure environments can occur in many environments.